Hello, everybody. Uh, my name is Daniel Silva, and I'm going to present our work titled Reinforcement Learning with Sun Differential Games, a case study on boost converter control applied to a nanogrid. This project is a collaboration between UFPA and the IFPA, and it explores how intelligent control methods like reinforcement learning can enhance the performance and robustness of nanogrid systems. It is a used control method for aerospatial systems, and we uh, try to test it on a boost converter. Well, so why do we need to intelligent control for nanogrids? Renewable energy sources such as photovoltaic panels are normally variable and they depend on solar irradiance and weather conditions. And in those nanogrids which integrate these sources, therefore require adaptive and robust control, is it's really nice when we use adaptive and robust control strategies to maintain stable operation. Boost converter plays a key role here. It is just like something that we are using to test it. Since into those nanogrids, it is used to step up the voltage to a stable DC bus level on our study here. And our main goal is to improve how that converter responds to some changes in radiance and load using learning-based techniques. And our idea is combines reinforcement learning with some differential games theory to achieve this adaptivity. And we compare with generalized predictive control. That is a technique that we are seeing so much into power electronics. And well, our objectives, the main objective is first to design a reinforcement learning based controller for a boost converter. Second, integrate some differential games into reinforcement learning to enhance robustness. Third, to compare the proposed controller with GPC, generalized predictive control, and to finally to validate everything through simulations under dynamic real-world like conditions. Our test system is a simple DC nanogrid with a 380 volts DC bus. Power comes from a photovoltaic source, which feeds a boost converter before connecting to the bus. On the load side, we have AC inverters, battery storage, and direct DC loads. But in our structure, we are just using the boost converter and controlling it to achieve a voltage reference. Well, thinking about the boost converter, we are focusing on the boost converter. It's the device responsible for stepping up the photovoltaic output voltage to the DC bus level. Uh, it usually operates in continuous conduction mode or CCM, and well, however, this component is very sensitive to variations in irradiance and load, which makes control challenging. And it's not properly controlled. These fluctuations can cause voltage instability in the entire nanogrid. So we gotta think and use a correct control method. And here in this equation, in these images, we have the boost converter structure, a basic one, and in this equation we have the transfer function used to model the controller. And what are those our control challenges? Basically, we have first the nonlinear dynamics. The converter behavior is not linear. Second, we have rapid Hodges changes, which happens naturally due to clouds or shading. Third, load disturbances, such as devices switching on or off. And those factors make real-time adaptability essential for any effective control scheme. So that's why normally people use a robust control to control those converters. And the idea is to use the sun differential games for that. When we talk about GPC, before we dive into the reinforcement learning, we are going to talk a little bit about GPC. Well, it is a model-based predictive controller built upon the Karima model, and it optimizes a cost function over a prediction horizon, which allows it to deal with delays, nonlinearities, and uncertainties of the system. It optimizes a cost function over a prediction horizon, which allows it to deal with delays and those problems that we have into the control area. In practice, we apply a hybrid version. We take this GPC and we put it into a logic from reference sequence tracking and from RST mode, and from that we achieve the gains for a PID control. So the idea is to make the implementation more easy. Like we have many structures there into industry that use PID. So when we take GPC and we make the same gains proportional to the gains from a PID, we make it more easy to implement into the systems. Here we have the cost function of this equation of the GPC, and the idea is to minimize that. Well, here we have the RST form and the PID gains from RST. They are commented into the paper, in the written paper. Well, when we talk about reinforcement learning for adaptive control, we have basically we don't need exactly the model of the system for this, because this method learns optimal control policies through trial and error, observing how actions affect performance over time. We use an actor critic architecture that is here in this image, where the actor decides the control action and the critic evaluates its performance. So we have uh, 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 those three blocks that make all the system works. This makes reinforcement learning particularly suitable for systems with unknown or time varying dynamics. Exactly our case in nanogrids, and that's why we use this a lot into the aerospatial area, because wind and some factors there, temperature, are really are big problems for us there. So when we use a technique that it adapts on depending of the noises and those problems, it becomes really well robust. And we are trying to test it into power electronics in this paper. Uh, well, when we analyze reinforcement learning enhanced by some differential games, uh, this concept comes from aerospace control, where systems must remain stable under uncertain and adversarial conditions. Here it helps reinforcement learning handle variability more gracefully. The reinforcement learning agent effectively adjusts PID gains using LKG, linear quadratic Gaussian inspired cost minimization, ensuring a balance between performance and energy efficiency. So we take basically the structure from the LKG, tune it with the reinforcement learning and some differential games, and we research a few articles that make this hybridization from LKG to PID. But when this happens, basically we have the adaptive PID tuning with key learning, that basically with reinforcement learning framework, we employ the key learning to iteratively adjust the PID gains. Each iteration updates the controller based on observed voltage errors and control effort. Over time, this leads to adaptive tuning, allowing the system to maintain optimal voltage even as the irradiance and loads change unpredictably. And this adaptability is what gives reinforcement learning clear edge over fixed parameter methods. Well, for our simulation scenario, most our mathematical parts are written into the paper. But our simulation scenario to test this controller, we have setups includes 400 watts photovoltaic panels feeding a single boost converter connected to a 380 DC bus, where we simulate the environmental changes by dropping the radiance at 2 seconds and again at 4 seconds, imitating like clouds passing or partial shading. And at 4 seconds, we also simulate a panel failure to test robustness. Initially, the voltage starts at 176.4 volts, then drops to 160.8 volts at 2 seconds, and further at 4 seconds, it down to 132.3 volts. And this simulation is made on Simulink, and we have here how we designed it. Since the controller is implemented as a PID, because GPC is hybridized to a PID, and the reinforcement learning optimal control also. So here are the PID gains standard with reinforcement learning in GPC. Uh, and here are basically the system responses from the system. Basically, the gains of PID are really close since the reinforcement learning achieved a good fit as really similar to the GPC. But we can check here that reinforcement learning gets a little faster into reference and with less noises. This close similarity of both sets of gains shown that reinforcement learning methods successfully replicated and even improved the performance of GPC-based tuning. When we analyze this, basically under these dynamic voltage drops, those controllers reacted effectively. However, the reinforcement learning achieved a faster recovery and smaller overshoot, especially during the second voltage dip. Uh, and well, when we analyze performance and robustness comparison, quantitatively reinforcement learning outperforms GPC. The ISA here, and it's a little smaller for reinforcement learning, and the square of the control effort ISU is also lower. So, in terms of error and in terms of control effort for reinforcement learning, we have a smaller value. But when we analyze the gain margin and the phase margin, both are similar and a little better for reinforcement learning, since it is a method that comes from linear quadratic Gaussian method tuning. So in this analysis that we had made, reinforcement learning achieves a better response, even in performance and in robustness. To conclude, our results clearly demonstrate that reinforcement learning in some differential games provides an effective solution for boost converter control in nanogrids in this application that we had made. It not only matches the performance of GPC, but also exceeds in adaptability and robustness. This makes it highly suitable for real-time and dynamic environments such as renewable nanogrids. As future steps, we plan to implement in real-time reinforcement learning on embedded hardware. So we want to implement it into a real system, integrate it with model prediction control and battery management systems, and explore multi-agent reinforcement learning for distributed control across multiple converters. Here are some references that we use for this article. And well, we would like to express our gratitude to IFPA, UFPA, CNPq, and CAPS for the support here for this research. And thank you for your attention.